Welcome to this presentation. I'm Auke IJsbeert, and I'll present together with Simon Hauser and Mehmet Mutlu. And together we'd like to present the Roombots project, which is our project about self-reconfigurable modular robots for smart environments. So as you know, this field of modular robots and self-reconfigurable robots is a very exciting field that started more or less 30 years ago in '88. With the SEPBOT project by Toshio Fukuda, who already started launching this idea of having little modules that can be plugged together to have different functionalities. And since then, many projects have been launched with the Polybot of Mark Yim and then many other projects, as you see here. And this is really an exciting field of research where this concept of Lego bricks and being brought to robotics and having the idea of having little modules that you can plug together to have very many different functionalities. So very exciting, but sometimes people are still looking a bit for applications. So one application we have in mind is to create a whole smart assistive environment. And our dream is to combine ideas from reconfigurable robotics together with assistive devices, cobots, and smart homes to create a whole smart environment to be assistive. And our dream is really to assist people who have limited mobility. So imagine you are in a wheelchair and you are in a small apartment. It would be really fantastic if the whole furniture in the apartment could assist you. Meaning, for instance, going away when you move in your wheelchair, or if you lose a pen on the ground, have a robot in the table come and pick it up and bring it back to you, and have furniture just take place back when you have crossed the apartment. So there's really opportunity to bring these active modules shown in red here in environment and to make the whole environment smart. And our dream is to not only make this useful and interesting for people who have a limited mobility, but also to make it fun for the whole family. So that's a bit our dream of the Roombots project. So today we'll present a bit to you the whole project and start by showing a video of illustrating a bit the concept of the Roombots. So what you see here is our Roombots module, but basically 4 Roombots module attached to an IKEA table. And this immediately gives the opportunity to have modules that can move around and that can adapt to the terrain. And also by using the degrees of freedom of the modules, you can step over little obstacles and provide functionalities to a table. Here, by adding even a little arm and a universal gripper, it's possible to pick up a pen. And basically, that's our dream, giving functionalities by adding modules to the environment, such that you can do things like passing objects and have simple manipulation abilities in the environment. So our dream is to really use these modules in many, many different ways and embed them in the environment. So the talk will now start by going a bit more in technical details about the hardware, and I will now give this microphone to Simon.
All right, I will briefly introduce the Roombots hardware in the next couple of slides. So for this, let's look at the short video about what one module can do. So we see here one module, it consists of 2 spheres, each consisting of 2 hemispheres, these black and white transitions, and there are 3 motors inside that can cause rotations in the module. Then every module has what we call an active connection mechanism. These are retractable hooks that come out of some of the plates. And this allows one module to either attach to another module or to the ground grid structure that you see in this video here. So here one module goes down, closes its hooks into the plate of the second module and lifts it up to form what we call a meta module, which is 2 modules in series. So this sequence of attaching and detaching can be used to initiate a climbing sequence. So what we see here is an on-grid locomotion where one Roombots module approaches a concave corner and then attaches itself to the wall here and then uses this attachment and detachment of the active connection mechanism to climb up this wall. And the same principle can be also used to achieve climbing on a ceiling, where the active connection mechanisms allow a little bit for misalignments, but can still grip into the plates of the grid that we have here. So we see here in the next slide, we see an explosion view. So we have these 4 hemispheres and then 3 motors inside there, resulting in 3 degrees of freedom systems with 2 active connection mechanisms inside each module. And the complete module is visible on the right. So it is 11 times 11 times 22 centimeters, weighs around 1.8 kilograms. And currently we have 13 modules in the lab. Now, compared to previous versions of the hardware, we had to upgrade a little bit of the interior parts. So we switched from plastic gearboxes to metal gearboxes and also replaced some of the plastic 3D printed parts with aluminum. This made the module heavier, but resulted in a much more precise motion. We also include now absolute encoders on all of the motors to be able to control the motion precisely. Now for the ACMs, the active connection mechanisms, here we included new sensors. On the one hand, these also magnets that form a little bit of attraction when 2 plates come close together. And on the other hand, we implemented Hall effect sensors and infrared sensors, which give a little bit of information of if a connection is going to be viable when the 2 plates come together. And here, one example of how the integration of everything works in the case of the universal gripper. So we have everything integrated in these hemispheres, custom PCB, a small-scale pump, pressure sensors, valves, and then resulting in the universal gripper that you can see on the right. Concerning the electronics, so here we also follow a modular approach in the sense that we distributed PCBs in these hemispheres. So one module has 14 fixed PCBs that are connected with slip rings. And additionally, we have these 2x2 extra PCB options on the left side, a spotlight that we can use to illuminate places, and on the right side, the custom PCB for the universal gripper. Now, Roombots not only should interact with themselves, but as Auke mentioned, we also want them to be interactable with existing furniture. So in the current work here, we have these 2 objects, these 2 pieces of furniture, a chair that has 2 Roombots modules, so it forms a differential drive system, and this table with a gripper meta module attached that we can use to manipulate objects, and then this cube that is used for illumination purposes, as Clement will present later. Now we can also imagine additional passive parts, as in the rendered pictures on the right, to be integrated in tables or stools or even more fancy pieces of furniture. Now I'll pass to Mehmet, who will explain a bit how we use this hardware.
Self-reconfiguration is in the core of this particular field of robotics. And this self-reconfiguration can be done in many different ways. The user operator or designer can go for some optimal solution or something that can calculate faster, but not necessarily optimal or maybe not really finding the solution. Today, I will explain you our latest self-reconfiguration framework, which is based on conventional search algorithms. In first step is we are formalizing the environment and discretizing states. Discretizing states means motors, degrees of freedoms, can rotate to only predefined angles. ACMs can be only open or closed. And we are also tracking the positions of base locations of each module. We are also discretizing the environment. We assume a voxel space and we check voxel occupancy in states. In the search trees, actions breed new nodes, and these actions can be our discrete states. And our states, our action, for example, can be also a combination of 2 different motors rotating at the same time, which will be a combinatory action. For example, while approaching the concave corner, 2 motors need to rotate at the same time so that the Roombots module can approach to it, and this can also be modeled as a single action, since the command can be given in just single action. Search algorithms are known to be notorious in high degree of freedom systems, such as modular robotics. In order to make this self-reconfiguration framework to work, we do some tricks like pruning search tree such that the physically meaningless nodes are eliminated immediately. We are keeping history and avoiding loops since our environment is can exhibit some loops in the search tree. And we also came up with a heuristic function to guide the search a little bit better and faster, to find the solution faster. Here, for example, you can see 8 neighborhoods and 4 neighborhoods in 3D environment, whereas our Roombots modules, the voxels can move only to different locations, which is based on the motion model of Roombots. In addition to the self-reconfiguration framework, we are also proposing a solution for misalignment problem. As Simon mentioned before, we have local sensors, Hall effect sensors, infrared sensors, and some magnets that gives us information about docking position, docking location. If the module exhibits some misalignment, we can try to overcome this misalignment using our sensors. Here, I will show you demonstration of a few different tasks planned with our self-reconfiguration framework. The planner knows on the initial and final locations of the module and the environment. The task, for example, here, 2 modules starting from in the bottom ground and then trying to climb up. Here, it's a bit the opposite, but with 4 modules starting in the ceiling and trying to go down while collaborating whenever needed. As you can see, the modules are not perfect, and once in a while they need a bit help for aligning. Here, the blue region is where modules cannot really dock, but while collaborating, they can still pass to the other side. In this demonstration, we have 5 modules. Normally, we can carry only a single module using another one. But if 4 modules collaborate and creating a wall, then the 5th module can use this wall to climb even further and reach to a ceiling, which wouldn't be normally possible with a meta module of two modules. Now I will show you one of the most impressive demonstrations that we did so far, forming a chair using 12 modules. The system has total 36 degrees of freedom. It is planned in 6 individual steps. In each step, 2 modules, starting from their initial locations, they go to the final goal state. During the planning, other modules can move to make up space such that the 2 active ones can reach to the goal state. As you can see here, we are once in a while helping, especially in metamodel cases, but it can successfully form a chair, a complex structure. Self-reconfiguration is not the only thing important in Roombots. We envision Roombots being used in smart environments, so they need to interact with users. In the most conventional works, what we see, graphical user interfaces. Graphical user interfaces are good, quite functional, and pragmatic, but they may not be the easiest way how people can interact with such systems. I will show you 3-4 different ways how we envision we can interact with self-reconfigurable modular robots in smart environments. The first one is related with the shape representation capability. We are using modules that look like voxels, and then intuitively just voxelizing the space should work for our purposes. But if we have limited number of modules, simply naively voxelizing with large voxels immediately loses the shape information rather quickly. However, if we can come up with nice strategies, we can still make use of we can still preserve the shape information even with just a few modules. Let's see it in action in a scenario. Let's imagine where user wants to light an object. Then the user needs something like a desktop lamp. User creates the shape of the desktop lamp using a malleable material like Play-Doh. And then this shape is 3D scanned. Ideally, this 3D scanning should be immediate, not in this case. First, we voxelize this 3D scanned mesh with some fine voxels, and then this fine voxel grid preserves the shape quite nicely, and then we optimally fill it with larger voxels. That will be the modules themselves. And then, once we know initial and final states, self-reconfiguration framework, just like the one that we just presented, can plan the actions needed for the task. Here, the desktop lamp is formed and the illumination light shines on the object. Such user interface can even be extended for continuous operation. Once it is formed, user can keep still moving the Play-Doh, and it can still keep controlling the structures. It's not limited with only malleable materials. You can use any passive object such as Lego or just wooden blocks, and then you can create very different, more complex structures. Let's look at another user interface. This time it's a virtual reality interface where user just interacts with Roombots in a virtual environment. Here you can see the user is using only hand gestures such as pinching, and the user can move objects around in the virtual environment, can pick up new objects and then align them accordingly, and then keep forming different structures. As well as active Roombots modules, the user can also pick passive modules and keep adding to create more complex structures, whatever is needed. In the end, those created shapes can be exported to different environments, such that the user can decorate a house, for example, change location of a table or chair. Yet another way to interact with Roombots or any self-reconfigurable modular robots would be using hand gestures directly. In this case, the user wants to change the location of the light. Roombots is carrying a spotlight. The hand gestures, hand location of the user is tracked with an overhead camera, and Roombots is simply shining the light on where the user wants the light. There is some open loop kinematic modeling as well as active control to compensate for small errors that's occurring due to misalignments. User is interacting only with light. However, in the background, there is some computation and other things going on, and those things can be hidden from the user. Here you can see what's happening on the background. There's simulation and real control happening at the same time. With similar ideas can be applied to not only tracking the user, but also tracking Roombots structures. For example, Roombots can actuate a chair, and this chair can be following the user, depending on the needs of the user. For example, if user falls, a chair can approach the user, and user can use it to lift himself. Alternatively, the same thing can also be applied for evading maneuvers. Now I will give the mic back to Simon. He will explain you our new hardware.
Yeah, so lastly, we would like to present you a teaser of a new hardware that we were working on that can be either as a standalone new system or possibly be integrated with Roombots. So the idea of our new hardware qubits is to do self-reconfiguration without moving parts. That is, without any mechanics really inside the module. And the reason we want to do this is because the mechanics of Roombots are complex, and of self-reconfigurable modular robots in general usually are complex and expensive and fragile. So our approach here is we developed a programmable magnet to do self-reconfiguration without these moving parts. This magnet consists of a soft alnico rod, and there is a copper coil wrapped around it. And by sending short pulses through this copper coil, we can influence the magnetization of the alnico rod, as in the diagram in the middle. So we can go from plus or minus magnetization, and we can also reach a middle state where there is no magnetics anymore in the rod. So we put this magnet into the edges of a cube and have 12 magnets in this cube. And now when two qubits modules connect, they form magnet pairs. And by choosing now the magnetization of these magnetic pairs, we can achieve, for example, attraction, which we use to do connection, or we can put the magnet pair in a neutral state to have disconnection, or we put them in a repulsive mode, and then they cause a pivot around one of the other edges. The module is very lightweight now. We only have our 17 grams. This is without electronics at the moment. It's prototyping stage. And it's very fast. The pulse lengths are between 40 microseconds to 100 milliseconds. So here is a slow motion video of how this looks. Couple of flips. This is a forward flip. Then we have an up to down flip, a down to up flip, and a sideways flip, and the ceiling flip. And here a more tricky situation with a trickier upwards flip. So in the next video, I invite you to focus on the right side where these flips happen in real time because they happen quite fast. So they are the same flips, but just, much faster. So some of these experiments we performed with just 3 magnets inside one cube to have a bit reduced weight conditions. And here we can, for example, achieve this trickier upwards flip. But some of the experiments we actually did with the 12 magnets, and they didn't always work. For example, here we cannot do the upwards flip anymore, but we still achieve the forward flip, as you can see here. So this is part of an upcoming publication that hopefully will come out very soon. And here, one more video that we can actually have a jumping mode if we control 2 magnet pairs at the same time. Okay, now we'll pass the mic back to Auke with a few closing remarks.
Yeah, so we hope you enjoyed this. We wanted to present in this grand vision of making a whole environment assistive. And even if we have been working on this for quite some years now, I still feel we're at the beginning. So there's still, I think, very exciting challenges and interesting challenges still to be tackled. The first one is related to distributed intelligence, how to really have local intelligence and to do more distributed reconfiguration, manipulation, locomotion. Many aspects we have shown so far are more centralized with the PC knowing where the modules are. And in the future, you want to distribute that more. Another thing which we should look into more is how to relate to Internet of Things and smart homes. So how to create protocols that you can interact with other devices. Machine learning, there are still many interesting things to do there to improve performance over time. And also this notion of human-robot interaction. As Mehmet has shown, we have already some interesting ideas of how to do that. One of my favorites is this Play-Doh because it's very intuitive way of interacting and creating furniture, possibly even moving it and using it as a tangible interface. But it's still not clear to us how to do this with the whole environment, how to have the whole environment being assistive, especially if this is done with people who have no technical expertise, so just lay users. So that's still a big challenge and I think a very interesting one. And finally, it's also very important for us to make things beautiful and have a good design to make this aesthetic. And we still have to work on that. And also to make it comfortable, and the ergonomy of the modules are important. Finally, one very important message is everything we do here, we feel it's transferable technology in the sense that many components can be reused for quite different applications. And the first one that comes to mind is maybe in space. Why not have a space station, a satellite, or a planetary station that reconfigures itself and has different functionalities over time, possibly be done remotely. Reconfigurable factories, having factory lines that change over time, or reconfigurable spaces like lab spaces or office spaces. I think there are many exciting opportunities where we like to use our modules for many things, and we are very eager for collaboration, having people help us to collaborate and work on this. So that's it. I hope you enjoyed this talk. To finish, I would like to thank the funding, first of all, that has supported this, and also all the people who have been involved in this for several years. And You see the faces here, and I'd like to give special thanks to Alex Pruvitz and Rico Muckle, who were the first one to launch this project in the lab. And just to conclude, if you want to see again the videos or get access to the papers, on every slide there was a paper, normally a link of the paper where you have more technical details. Please have a look at the website that's here given at the bottom of the slides. So that's it. Please come to us if you're interested in collaborating or if you have questions. And otherwise, thanks a lot for your attention.